next speaker, I'd like to introduce Dr. Roman Marchant. Roman is a senior research fellow here at DARE. He's a self-confessed Bayesian computer scientist. His current research focuses on developing new data science methods to answer complex questions regarding decision-making under uncertainty. And I understand Roman is going to be talking to us about air pollution today for environmental monitoring. Thanks, Roman.
Hi, Sally. Thank you for the introduction. As you've mentioned, I'll be talking about how do we monitor environmental phenomena that's changing over space and time. And there's a technique called Basin Optimisation that I actually studied during my PhD, and I've continued to work on it since then for approximately 5 years now. So I'll start talking about Gaussian processes, uncertainty, and Basin Optimisation, and how we use that to model and make decisions in the real world, and the applications to monitoring environmental phenomena. This includes ozone concentration and multiple other applications that I'll show you. And what is the future in terms of the developments that we're looking at doing in the next couple of years and the future applications that we're tackling. So I'll start, given that yesterday everyone presented wonderful quotes related to uncertainty, I thought I will use this one by John Maynard, right? So it's better to be imprecisely right than precisely wrong. And I always tell that to my students when I'm teaching sort of like Bayesian inference and non-parametric modeling, what is the importance of uncertainty? And we've covered this, I guess, yesterday. All the speakers clearly outlined how quantifying uncertainty is crucial for making informed decisions. And it can also be helpful for driving the data acquisition process, as I'll show you in the upcoming slides, because you're able to quantify the risk appropriately and also do interpretation of the models that you build. So Gaussian process regression, I'll try to keep this relatively simple with not much maths in it, but the idea is to have some data. This plot on the right here shows the crosses some one-dimensional data, right? So you have X and Y, whatever phenomena you're monitoring, in this case, one-dimensional, and you use a covariance function, and that helps you predict the value of this function pretty much everywhere. So as you can see here in this animation, by maximizing, in this case, the log marginal likelihood, we're able to obtain a representation of the underlying function that we're trying to monitor. That is obtaining a mean, which is the expected value of the estimation, what most decision makers really rely on most of the time, right? So what is your expected value of pollution tomorrow, or your expected temperature tomorrow? But the good thing about non-parametric modeling, Bayesian reasoning, is that you can also quantify the uncertainty through the variance of these stochastic processes you can see in this figure. So this is this key concept of quantification of uncertainty becomes important in the decision-making processes that I'll show you. Now, just a little bit more of maths, right? What happens when you have a spatial-temporal, right, a more realistic process? Well, now you have a spatial and temporal component in your function that you're trying to model, and the Gaussian process now achieves this modeling through a spatial-temporal covariance function. The predictive distribution now can give you the expected value, as you see there, and the variance, right? All these complex sort of like algebraic equations allow you to compute this in closed-form solution if you have Gaussian distributions. Now, in order for you to understand, I guess, more about this, you're welcome to check the Gaussian process book from Rasmussen and Williams, which is pretty popular in this topic. So an example of this for environmental monitoring, right? So given, say, for example, ozone concentration in the US, there's multiple stations measuring ozone. And the idea is that if you place a spatio-temporal Gaussian process over this data, you achieve regression. That is a smoothing over space and time, as you see in the top right video. You're looking at the expected value of ozone in space and time. And on the bottom, you see the behavior of this regression over time. So the good thing is you're able to quantify both the expected value of ozone and the uncertainty in your estimations. But then, how is this used for decision making? And that's where Bayesian optimization comes in. And I'll quickly explain what Bayesian optimization is and how it is used for decision making, how it uses the uncertainty. So Bayesian optimization is in general a technique for finding the maximum of an unknown, noisy, and costly to evaluate function, the perfect application for environmental phenomena, things that change over space and time, right? The underlying latent process of pollution is not exactly known. It's very noisy, and it's costly to evaluate. You can't just do a grid search and install a sensor every 2 meters, right? So the idea is that you want to pick your next location to sample in a smart way by using this technique called Bayesian optimization. So this is the main algorithm of Bayesian optimization. If you're not familiar with algorithms, well, it's sort of like a loop that repeats over and over, and it uses the uncertainty to be able to make decisions. So as you can see in the figures here, right, on the right-hand side, we have the underlying function, the unknown function, which is the dotted line. It can be temperature, it can be ozone, it can be anything that you're modeling, in this case in one dimension, but generalizable to multiple dimensions and time, same as we did with the GP. So with this objective function, you also have your Gaussian process model, as I explained in the past, right? You have your observations and your uncertainty, which is the purple shaded area that you see there. The idea is that you can evaluate an acquisition function across this space. The acquisition function, as the name says, is the proxy for where to acquire the next data point. And this acquisition function, you need to optimize it in every step. So the first step of the algorithm, right, is to find the maximum of this acquisition function. And I've put an example of an acquisition function there, a popular one, which is called upper confidence bound. And it takes into account the expected value of the GP, the Gaussian process, and the uncertainty. So it will basically trade off between exploring and exploiting the current values of the function that you're trying to model. So the idea here is that by repeating this algorithm, you find the maximum of the acquisition function, and then you gather a new observation at that specific location. So where to sample next? Well, this method allows you to answer that question, and then you either send a robot to monitor there, or you install a new sensor, or you just draw a sample from the function at that point. You update your Gaussian process model. So as you can see there, the uncertainty around the expected value of the function has decreased. And then you can recalculate the acquisition function and keep repeating this process over and over again. As you can see that the samples will start concentrating around the areas of interest in the function. In this case, because we're maximizing f, it will be around the areas of maximum values of f. So that's the idea of Bayesian optimization. There's a book that has been recently released that I've put on the top right for everyone that wants to read a bit more about that. So let's talk about some applications where we've used Bayesian optimization in the past. This one here is an interesting work that we did with the South Australian government, where we were looking at all the points that you see there over South Australia are wells. So we're monitoring groundwater. And the idea is that we want to optimize the network, that is, select the locations that give us more information using Bayesian optimization. And the video shows basically, as you start removing wells, the uncertainty increases, which is the red. Red means high uncertainty and blue means low uncertainty. So by achieving this trade-off between the uncertainty chain, as you can see now, the animation is showing the mean estimation. By using both surfaces, you can decide which wells deliver better or more useful information and incorporate those or not into the system, right? Making it more efficient and also achieving better information. Same way you could decide where would you drill next based on reducing the uncertainty, right? Whatever the acquisition function that you're trying to model is. I didn't mention any more acquisition functions because I didn't want to put more maths in the presentations, but the book that I've referenced, you'll be able to find a lot of different acquisition functions that have an effect in terms of the decision-making process. This is another example where, so this animation shows a robot, a UAV. This is simulated data. It shows a UAV monitoring ozone as well in the US, some of the states that you can see as lines in the background. The good thing is that each row here shows different methods, right? What happens, the bottom one is the most naive one. What happens if you have a UAV just monitoring randomly the environment? It doesn't necessarily follow, it's nothing smart, and you can see it's very chaotic and not very efficient. Whereas on the top line, you can see that's the upper confidence bound, so a specific acquisition function using Bayesian optimization for the paths. And you can see the behavior of the agent. It automatically starts first exploring the environment, and as it starts finding where the expected value of ozone gets higher at specific points in space and time, it will repeat, it will sort of like come back to those locations to sort of like improve its understanding of where pollution in this case is the highest. So that's great because we've sort of like obtained a fully sort of like autonomous decision-making system that will explore and automatically start exploiting its knowledge to find whatever we're interested in this case, high ozone pollution. Now, we've also done work about multiple step look ahead decisions, right? In this case, this is the expected reward one step look ahead, right? So the expected reward takes into account the uncertainty through the posterior distribution of the function f. And what happens is we've done work to estimate the sequence of decisions that make each one of them optimal, right, in the perfect scenario. But we obviously weren't able to calculate that exact solution because of the complexity, and we are able to approximate it. So the full solution looks like this, right? We start expanding the one-step look ahead, and we need to start considering now n steps in the future. So as you can see now, we have a sum of the rewards up to step n, and we are integrated across all the possible values of f in the future, right? So it's if we properly quantify the uncertainty over f, we're basically marginalizing out all the possible outcomes of the environmental process to take the decision, which is great. Now, this is a very complex term that you see on the bottom there. I spent around 6 months trying to figure out, I remember during my PhD, trying to figure out how to calculate this integral exactly. I wasn't able to find a solution, a closed form solution. So we used Monte Carlo tree search, which is a technique for sequential decision making. And we figured that by using this technique, we could approximate the solution of this n-step look ahead process. Now, we applied that to monitoring spatial temporal crime. In this case, this video here shows Basin Optimisation for predictive policing. Essentially, you can see police as a sensor of crime, right? If they're patrolling around and finding crime in different locations. And the video, the animation that you can see now playing, shows a police car wandering around the city. But the key thing is that the decisions that this police car is making are informed by the expected value of crime. But not just that, as usually police does, but it's also using the uncertainty. It's using the posterior uncertainty of the Gaussian process as a proxy of, not knowing what the crime levels are in that area and driving to that area. So basically, as you can see on the bottom right, the top is the ground truth of crime, right? The with known hotspots, but obviously the police car initially doesn't know what these hotspots are. And basically the bottom plot is showing as color the predicted mean. So what at that point in time, what the police believes is a high crime area or low crime area, and the uncertainty is the transparency. So if we continue watching this video, we'll not be watching it for 5 minutes, don't worry, I'll actually make that a bit quicker. But ultimately what happens is that the police car starts exploring the environment, but it'll eventually start focusing more on the areas where there's higher crime. So achieving a balance, a trade-off between exploration and exploitation driven by uncertainty and the expected value. So as you can see here, what happens when you start tuning your parameters and your acquisition functions, you get different behaviors of the agent, right? You can see that if you set the parameters in the acquisition function to be favor uncertainty only, you will achieve the center plot, the trajectory that basically covers the entire region, sort of like a maximum coverage solution, just reducing the uncertainty. Where you can also go to the other extreme, which is don't care about the uncertainty and just go to where your expected value is higher, so where there's more crime. And usually that's what police do. They basically go to the areas where they think they're going to find more crime, but they don't really formally take into account the uncertainty as a proper spatial temporal model. So that's what we're trying to improve here, is by achieving a trade-off between exploration and exploitation. You would want patrolling routes to explore the environment and also focus on the areas where there's potentially more crime. So exploitation, exploration, trade-off again. And I guess the idea is that these will ultimately reduce over-policing, particularly in the areas where police doesn't know how much crime it is, they'll eventually figure out. So these are other very interesting applications that I found of people citing our papers that have used similar techniques for real-world environmental processes. So the example on the top left is plant disease, right? So there's trees and they become sick, and strapping hyperspectral cameras into UAVs, people have found that using Basin optimization, they can actively monitor disease. They can also, on the bottom, you can see a drone monitoring gas leaks for pipes in deserts and so on. You can also see applications of drones monitoring the seafloor and even nuclear plants where humans cannot go in. You can deploy robots using Basin optimization path planning to make autonomous decisions, right, based on uncertainty. So where is the future going? What are the sort of things that I'm interested in exploring? Bushfires, right? So at there, we're working a lot with the environment, right? When we really want to understand the environment, and in order to do that, we need to make decisions, right? And bushfires, everyone knows how, you know, a terrible bushfire season we just had over the summer. And the idea that we have is to be able to use drones ultimately, or other sort of like mobile sensing agents that can automatically decide where to go next to better understand, for example, how the fire frontier is expanding. Now, this involves a lot of spatial very complex spatial temporal modeling of multiple variables, including wind and temperature and smoke, and using satellite imagery and a whole bunch of complex stuff that we're working on. There's other projects that you can think of, like sequential drilling, which we'll be working on in the near future as well. So sequential drilling basically involves deciding where to drill next. And we're also doing fish biomass estimation at the moment, just estimating with existing data. But we started thinking also of how you can use basin optimization to decide where to deploy sensors to better understand fish biomass in the vast extent of the ocean, right? So you can imagine this is a very complex spatial temporal process where we are placing sensors in a smart way, driven by uncertainty, to be able to capture the underlying unknown process. And lately, there's also been a lot of hype around, obviously, COVID-19. We've done a bit of work on COVID-19 as well. And we've been exploring the ideas about basin optimization, fostering testing on specific regions to be able to detect outbreaks before they happen. Ultimately, this involves a lot of challenges from the data science perspective. My, I guess, particular interests around the data science challenges that these applications bring to the table are studying what happens when you use multi-agent systems, right? We've looked a little bit about that, but there's a world of opportunities and new developments that we need to achieve to be able to use a swarm of robots or police cars to better understand crime. Non-Gaussian priors is another very important advancement that we need to tackle. We've looked at Poisson process in the future. In fact, crime is just count of crimes. It's not a Gaussian distribution anymore. So we're looking at solving these problems as well, and dealing with non-stationary processes, which are really complex, and heteroscedastic ones as well, where the noise changes depending on where you're measuring, right? So you imagine the noise, or just the process error, or the noise, the inherent noise in the process changing if you're close to the bushfire or far away from it, right, for example. And also understanding how, you know, causal inference could be better understood using Basin optimization by looking at the effective intervention. For example, in the bushfire case, can we understand how making decisions like backburning or deploying different resources in different regions can mitigate the extent of bushfires? So basically, I guess in summary, I guess I've shown you a framework for using basin optimization, non-parametric modeling, to be able to quantify uncertainty and make informed decisions. Thank you.
Thank you, Roman. It's for a very interesting talk. I would like to remind participants that there will be a quiz at the end to make sure that you can reproduce the solution to that integral that Roman put up on the board.